Hello and welcome to another AP Physics 1 review video. This topic that we're going to look at is actually going to go ahead and look at two ideas, but they're very much interrelated, and there are many AP problems. They show both these ideas in the same problem. It could be even multiple choice question. It could be a free response. The ideas of both energy and momentum. So that's what we're talking about today. The ideas of energy and momentum. By definition, those two things are fundamentally different. Energy is the ability of something to do something. That doesn't sound very helpful, but basically saying that if that object has energy, it can do things. And because it can do things, it can transfer that ability to other objects. Really, when we say its ability to do things, when we say doing things, we're really talking about the idea of work. Work is the ability of an object to transfer energy. And we'll talk about those ideas a little bit more. And the ideas of momentum. Momentum is mass in motion. So that's a quantity of not just an object, but an object in motion. The big thing is momentum, that's something that an object has, but it needs to be moving in order to have that idea. Energy is something that an object can have, but it needs to be in a couple of different forms. It doesn't necessarily need to be moving, like we talk about the ideas in terms of momentum. The other thing we want to think about is there's that idea of something called conservation. We'll talk about that in this video as well. Conservation means that things remain the same within a system, not just the same, not just constant. When we say conserve, conserve means multiple things being the same within the system. So first off, we're going to spend some time on energy, then we'll talk about the ideas of momentum. Okay, energy. We can have this in a couple different forms. One is in terms of moving energy. We see K equals 1/2 mv squared. That deals with the idea of kinetic energy. We can say U sub G, that deals with gravitational potential energy. U sub S, that deals with the energy stored in a spring. We deal with the work being the change in energy. And it has some weird stuff that goes along with force, cosine, angle times the displacement. And P is power. Power is work over time. The units for power are watts. The units for work and energy are joules, and T being time. So big ways that you can see this are if it's a problem where something is lifted, it's screaming energy. So if you have something being lifted to some position, it's screaming energy. Why is that? Because it doesn't matter what happens in terms of how things fall or on a curve or anything like that. As long as it covers some vertical distance, you're going to have some energy stored in gravitational potential. So big ways that this can be shown in problems are a couple different ways. One way we can examine this is if we take any type of object and we take it and we lift it to some vertical distance. And it's located here. So let's say it's a ball of mass m and it gets located and positioned up here. First off, you should realize if I have this increase, if it's pushed up here, that means that there is some change in energy done. What would that be equal to? Well, that's work. Work is change in energy. You can even find on the AB equation sheet, it shows delta E is equal to W. What does that mean? Change in energy is work. So if we lift something, we have energy added to it. Now, it's the same amount of work if I just go and lift it like that versus like this, bring it back down, then up here. Because that D is not just X, not just Y, it is displacement. So it deals with the difference between start and end positions. Now, classic AP questions not just deal with lifting something, but they go ahead and say, okay, something's sliding out, something's moving, and different things happen. We could go ahead and say that we have a block on a ramp like this, and it goes ahead and slides down. These are similar to some problems that we looked here in class. And this thing slides down and moves here, and we've got a spring attached at the end. Say, okay, how can we look at this problem? Well, if it gave us this vertical distance, and we called it OH, and it slides down this ramp, slides through here, and smashes in that spring. We were to say, okay, by how much does it go and compress that spring? Without even using any type of numbers, we can think about what's going on in terms of energy. Now, looking at this, you say, okay, well, wouldn't there be force friction and things like that acting on the system? Yes, but if we say force friction is equal to 0 here, we can simply say, okay, the initial energy is equal to the final. So if force friction is equal to 0, that means the initial energy, is equal to the final energy in the system. But if force friction is not 0, then those energies are not equal. Then how do we account for that? Because there must be work done. In this case, the work done would be done by friction. Now, in many types of problems, you have to think about what this part means, this cosine of the angle. That angle deals with the angle between the displacement and the force. So in terms of like on a flat surface, and something's being pushed like this, and that's force normal. The angle between those two is 90, and the cosine of 90 gives us 0. So that means if I push something that way, there's no work done by force normal, which makes sense. Now, going back to our original idea, yes, we could say the force friction going against this, but what if we just go ahead and, to make things easy in terms of review, let's go ahead and say, okay, E naught is equal to E. So force friction is 0. No force friction shows what's going on. How can we find how much that spring is compressed? And you say to yourself, well, is it going to have to go down the incline? It's going to be accelerating, and it's going to be coasting at constant speed this way? Yes, but the beauty of this stuff is if we just deal with energy, the problem of that going down an incline and flattening out doesn't really matter. We can just say E naught is equal to E. Now, when investigating this idea, all we have to say is what energies do we have at the end and at the beginning. So with this being said, UG naught, the initial gravitational potential, plus K naught plus US naught, the energy stored in the spring initial, is equal to UG plus K plus US. Now, if we take that as our initial, take that as our final, that means that initially it is not moving, there is no spring compression. That means at the end, no more gravitational height, and it will indeed be stationary. So that means no matter what's going on in this situation, all I have left is UGO is equal to US. What does that mean? The initial gravitational potential is equal to the stored spring energy. So that means mg delta y is equal to 1/2 kx squared. Now, in this term, you notice yourself, yeah, that looks kind of ugly how we have it set up, and it doesn't seem like there's all that many different ideas that would cancel out. So we could solve for x to show that idea? Well, certainly we could. We'd also see this as a function of the relative height at the beginning. That if we have this thing increasing, this part would be increasing as well. Say, well, how much? It would be a multiple of root 2 if you think about it in terms of that being squared. So if I was to rearrange this, 2mg delta y all over k root would be equal to x. And say, oh, cool, okay. So again, talking about that root 2 idea, if I was to double that, right, that distance would increase by a multitude of root 2. Why? 2 square root, if I pull that out, I see that would be root 2 in terms of multiple what's going on there. So it would not be an increasing proportional distance. It would be increasing, yes, but it would not be directly proportional as we see here. Again, if stuff is lifted up, it's screaming energy stuff. That's what it's looking at. The other part we want to deal with is this, force cosine the angle times displacement. In these two different topics, you can see two graphs that are very similar. Now, if you see a force distance graph like that, and it says, okay, something's moving at some rate and some force and distance are applied to it, what's the new speed? What is the new speed? You should be thinking energy, because if I show this thing, right? So this is saying there's a box that's stationary and I push it just a little bit. Or if it was moving and I push it, I show a force like this. And you say to yourself, well, how would I find out how much it's speeding up? Well, work is equal to change in energy. So if it was moving and I push it more, it's just not any energy, it's change in kinetic. How do I find that work done? You say, oh, I've got a changing force, right? And I've got a distance. How would I find it? Notice, as long as force and distance are in the same direction, that means the angle between them is 0. So cosine of 0 gives me 1. So this turns into force distance. So how can I find that? Area under the curve. So on an FD graph, work is equal to the area. Big idea for work and energy stuff. Okay. The other part deals with momentum. Now, in any type of collision, in any type of system, we're always assuming that momentum remains constant, unless outside forces are present. Here's the thing. We could have momentum conserved with energy not conserved. Momentum always conserved, but energy can be left from the system. What does that mean? In terms of energy being left in the system, it'd be lost to the surroundings, but momentum is always conserved. P equals mv. That's our mass in motion, inertia in motion. Big way that these type of problems happen are in terms of collisions. So, give me one moment to readjust here. In terms of momentum, it's mass times velocity, right? So if I have an object, well, let's say it's a box and it's sliding that way. We'll even do this on one dimension to make things easy real quick. And this has some m and this has some v, and it smashes into a stationary block. This has an initial velocity of 0. If this goes ahead and moves like that, and that has some velocity 0, if these two things go in and move, if these two things move like this and smash into each other, we should realize that they're going to have to slow down. And why does that happen? Because of that change in momentum. If this would be m1 and this would be m2, m1, m2. How can we find the final velocity of the system? This would be something known as an inelastic collision, because we're talking about them hitting and sticking together. Now, depending on what's going on, if it was to say that it's a completely elastic or inelastic collision, you have to deal with energy stuff. Elastic means that not only is momentum conserved, also energy is also conserved. So elastic means not just momentum is conserved, but that energy is conserved as well. So we can still apply that idea as well. But inelastic doesn't necessarily mean that they just stick together, but it also means that energy is not completely conserved in the system. What does that mean? Things can heat up. So in this particular situation, how could you find out what's going on here? We can deal with the initial amount of momentum in the system. It's equal to the final. So if I make that 1 and I make that 2, so m1 v1 naught plus m2 v2 naught is equal to m1 v1 plus m2 v2. Now that looks all kinds of ugly. We've got all kinds of subscripts in this stuff. We could do this in two-dimensional planes. We could do it with momentum in the x, momentum in the y. Yeah, but in this case, we're just talking about straight line. In this case, this thing would be 0. Afterwards, they're combined. So we're going to see that, okay, they have total momentum that will be shared. So they have the same final velocity. So m1 v1 naught be equal to that. So how could I find out what's going on here? If I was asked to find their final velocity, I could have something like that to find out what's going on. Now, not only is it applied in the x, but also in the vertical. What do I mean by that? If it was something more moving like this, and two billiard balls hit, two polo balls hit, and I have one going this way and one going this way, this would have some momentum in the x. This would have some momentum in the x. And they have momentums, separate momentum in the y's. How does that cancel out? Because momentum is a vector quantity. So if I momentum this way and this way, the addition of the two would still yield 0. Now the other part of this deals with graphs in terms of momentum. And this is, again, we're talking about a force distance graph showing area underneath it to deal with work. If we look at a force time graph, I say force times time. If you think about force times time, that would deal with a change in momentum. That's an idea of something called impulse. If you look at force times time, that would deal with our change in momentum. So a force time graph shows delta P. So force time graph shows change in momentum. 3 big things out of this video that you should remember that are going to come up on AP style questions. 1, if it deals with change in height, it's screaming energy. 2, if it's a force distance graph, it's dealing with work. 3, if it's a force time graph, it's dealing with change in momentum. As always, I hope you enjoyed the video. I'll see you in the next one.